my research. I do research on protein structure and biological system. Most of the methods that I'm using are shallow or conventional learnings. But I think 3 other speakers today will give more details about deep learning. But I'm going to cover a superficial aspect of the deep learning, but I'm going to more focus on the paper published January this year about AlphaGO. And I read this paper many, many times, and there are some technical difficulties to understand. Sometimes the paper in the article contradict with the data they provide in the supplementary materials. So, but I'll try to provide the best picture of the AlphaGO and how it works and how. I did some Google searching on AlphaGO principles, and I found many presentation files provided by English people and also Korean people. And I found also some things that does not match with the paper in the Nature. So I'll discuss all those. So the paper was published January of this year in Nature as an article. It's quite a long paper. And this is, okay, so I'll follow the paper, okay? So if you think about a game of perfect information, meaning that both players know all the information at any moment. If you think about some game where you roll dice, that's not the perfect game of perfect information. Or anything, some information is hidden, like in the StarCraft or poker game, they are not game of perfect information. And in this game, you can define a value function. Here, S is a state. It's a board state for any moment. And for a given state, a situation, and you can define this V star. This is the optimal value function on the perfect play by all players. So if we know this, it means that from the start, we already know that if the black will win or lose. Okay, I know that this 고목구, 오목 in Korean, this is basically solved. So the first, player will always win in all situations. So in Go or in chess, the complexity of this, you have to do the search tree. In this case, the search tree, this is approximately b to the d power of d. And b is the breadth. Each moment, how many possibilities are there, and how many moves it's going to require to finish the game, the depth. And it's roughly 35 to the 80s for chess, and 250 to the 150 for Go. By the way, the Go is also known as Baduk in Korean or Weiqi in Chinese. So basically, exhaustive search or enumeration is infeasible. It's not possible. The fastest computer as of today can execute maybe 10 to the 16th or 10 to the 17th operation. So what they do is that they have to reduce this search tree in 2 ways. First, you want to reduce the breadth. So as humans play the game, they don't consider all possible beginning moves. There are only a handful or tens of beginning moves, right? So you have to somehow reduce the breadth of this search tree, and also you have to reduce the depth of the tree. Okay. And lately, okay, so first, I have to explain the concept of rollouts. Some people call it rollouts, or some people call it playouts, meaning that you make up your policy, and just following that policy, you are going to play the game to the end using this policy. Okay, And often this policy suggests more than one move with probability. So you can think about Monte Carlo rollouts as a method where the breadth is 1 and depth is maybe 300. So the tree will be just very deep but very narrow tree. And recent breakthrough in the artificial intelligence or in the game study is the Monte Carlo tree search. So they combine this Monte Carlo rollouts with Monte Carlo tree search. I'm going to go in details about this. And then I'm going to go into detail about this twice. Okay? First, in the context of general game playing. And later I'll go through this in the context of AlphaGO. Okay? So this was a breakthrough in the game theory of games. If you have any question, you can always ask me. Okay. So Monte Carlo tree search. This is not the AlphaGO's. Okay.
So could you give us an example of a policy?
Yeah, I'm going to.
Yeah, I mean specific.
Specific.
I understand.
Okay. Yeah.
I want a very
concrete example. So one easiest is just to play random. Yeah, play random, any evenly, or you can in the game. In the Go, there are some known rules, like in this situation, what is the best, and that kind of thing. Okay, so you just apply few rules. You can also apply machine learning method, where you have many. They use machine learning method to choose the probability of playing each position. Is that specific enough? Okay, yeah. So think about random play. Random play. Yeah, random to the end. Okay. Okay, so tree looks like this. Okay. So in the tree, Monte Carlo tree search, there are 4 steps you have to follow. The first one is you have to. So here, this is a root node. So each circle represents a node, meaning a board position. And arrow, the line is the edge. Edge is the action that you can take. Okay? So at the beginning, maybe empty. Here it shows 3 possibilities. This comes from the policy. Okay? If you think about random policy, you will have a 365 branches branching from here. Okay? But if you think about a more simple policy, more sophisticated policy, then you can have multiple, like less than 361 moves. Okay, and then you follow. You choose one of these suggested moves. You can choose the highest probability moves, or you can just use a random number to select your move. And then you go to the end. You decide how many steps you want to go. Here they say L steps, L moves. Okay, so here the nodes at the end is called leaf node. If you think about tree, big tree, at the end of the tree there's leaves, right? So this path, selecting this path is called the selection process. So at the first time you just select one path, okay, and you choose another path and so on, because the path is selected in the Monte Carlo tree search according to the random numbers. Okay, and once you reach this leaf node here, then you have to evaluate this leaf node. You do that by following fast policy. Okay, because here you have to do many moves to go to the end of the game. Okay, so here you always go to the end of the game using policy to both players. In the Go, white and black finish the game using the same policy. Okay, and then you will know the outcome of the game. And this is, I mean, you can use Monte Carlo rollouts. Okay.
The policy just needs the rule.
Yeah, it's a rule. So if you give a board position to the policy, then it will give one potential move. Okay.
Just one.
Yeah, one, and then I mean one is chosen out of according to their probabilities. Yeah, but here they do only once, one game. Okay, if this reach to here again, it can reach here by just following the same path or different path. It will do the second rollout. And the result may be different because rollout also use random numbers. Okay?
So what is rollout exactly?
Rollout is play till the end of the game using the same policy, alternating between white and black. Okay? It's very important that you have to use the same policy. Okay? So this is finishing the game. So here, basically, you can think about this one also as a rollout, but only up to the leaf node. Okay, and the second, this one is usually one by one. I mean, few steps, or few tens of steps. But here you have to go all the way to the end. Okay, and here you can use different policies, how to reach to here and how to reach from here to there. Because this, you have to do this many more times. Typically, hundreds of more times than what you do here. I will come back to this point. So usually they use very fast policy for this rollout, and they can use a slower policy for this selection. So in AlphaGo, they use deep learning-based policies for this policy sigma, and the shallow learning for the fast policy. Because fast policy is about 1,000 times faster than deep learning-based policy. Okay. And once so here you already know the game result, right, based on this policy. And this information is going to update some weight in the edges that it followed. Okay, so this weight in the edges will be followed. This will effectively change the policy of the selection. Okay, and you do this many times, and you will have at the beginning you have just one leaf node, and if you do it a million times, maybe you can have thousands of leaf nodes. And some of the nodes are visited more frequently than others. So if some nodes are, the visit count is bigger than a certain number, here they use 40, then they can expand. Okay, here? So it shows the expanding here. So here, expansion also requires a policy, because there are many possibilities. Okay, here. So in the AlphaGo paper, they use 3 policies for searching. But in the paper, they discuss only 2, and the third one is included in the method section. Okay. So these search policies are all learned by supervised learning, meaning that you give an instance and the label is always given by label. Okay, and the first one I told you is can you turn off the heating? It's too hot here. So this first one, P sigma, is learned by deep learning, and the other 2 is by shallow learning. So deep learning, this method requires about 3 milliseconds. I don't know whether this is 1 GPU or 1 CPU, but probably 1 GPU, 3 milliseconds. So you can do like thousands of this in 1 second using 1 GPU. And the other one is like 1,000 times faster. Yeah.
So this is happening at the learning stage of this rather than actual game?
Yeah, learning, they did about the whole learning took 5 weeks. But you know, the game with the Fan Hui and Lee et al., it took just 1 hour for AlphaGo. Yeah.
Basically, they accumulate data so that they have a value to particular thing or tree.
Yeah, so after 5 weeks of learning, everything is set. And I'm going to discuss this at the end of my talk, but they didn't do anything special for Lee et al., or it's impossible, basically. Yeah. It doesn't help them. Yeah.
So basically, this is a loop. So you said till the end of the loop, right?
So basically, based on this information, it will decide which action it's going to take.
Right.
Okay? Yeah.
For the second one,
Mm-hmm.
number 2. So it's playing till the end.
Yeah, here.
Basically, this is a loop. What is going to be the condition to end? How do you know?
So the policy will decide. So they will pass. So there's no place that they are going to gain any point. Then they can pass.
So if you play Go,
Hmm?
the random move, you play until it completely fills the, not exactly, but you fill the board.
Yeah, but they are not doing the random move. Yeah.
Unless you do something.
So it always assesses the current situation, and whether it assesses all the moves that is going to help them help it or not. So at the end of at the end stage of the game, it passes the move, and because it's playing against the same machine, it will pass, and then that's the end of the game. Okay. Okay.
I'm sorry, I just wonder if you have any kind of questions like that Monte Carlo research has already generally used in the game.
Yeah, this is a breakthrough in the game, I don't know, industry or the computer game strategy. By the introduction of this Monte Carlo research, before this, for example, Go, this can be applied to any games. And in the Go, the strength, the current, before the AlphaGo, strength was about amateur 2 dam. Before it was like only several stones weaker. But just applying this, this is the first breakthrough. Go very strong. Yeah. Hmm?
I remember that the previous versions of Go software also utilize MCCM.
Yeah.
But they say that the difference is that they introduced the point method.
Yeah, why don't you wait until I explain? Yeah.
Curious.
Hmm.
Does it correspond to any of like T sigma or T pi or T tau in there?
Yeah, so this here I'm just describing the general concept of, but I gave a little bit of taste of AlphaGo. Yeah, so AlphaGo used 3 different policies.
And T sigma corresponds to the point method?
It's a P means policy. Yeah. So yeah, so here I showed you 3 different kinds of policies because there's 3 different kinds of actions. Yeah. Okay, selection and rollouts and expansion. If you want, you can use the same policy. Yeah. Okay. So if you have a question about AlphaGo, why don't you wait until the end? Because I'm going to cover all of them. Yeah. Okay. If time allows. Okay. So what they did here is that the important thing is they used deep learning to generate their policies. Okay. Only the selection policies. And they used convolutional neural networks. Okay? And as you know, conventional neural networks or support vector motions, they are all shallow, meaning that they have only 1 or 2 nonlinearity processes. Okay? So I hope that this details about deep learning will be covered more thoroughly by 3 speakers today after following my talk. Okay. So this deep learning is especially useful, they say, for image processing, anything related to imaging. I also use machine learning for studying protein structure and sequence analysis. And as far as I know, the performance is not great. I mean, much greater using deep learning. I could be wrong, but that's my understanding. So deep learning requires much longer computation for learning, training, and also for computing the situation. Okay, it's roughly in the AlphaGo, it's about at least 1,000 times slower. So they cannot use this for all the policies. Okay, so as I told you, they use the three policy networks here. The first one deep, and the other one shallow. The other two. Okay, so here they say that for the most important supervised learning policy, it was trained using games downloaded from Go server, I think in Japan. Okay, so here basically they have about 160,000 games downloaded. This one is about 30 million positions. And this is played by 6 to 9 dan player in KGS. Some of them could be professional, but officially they are all amateurs, very strong players. So none of the official professional games were used in AlphaGo training. Okay? So they divided this to 28 million positions for training and 1 million for testing. So each position has this two components. S is the board position, and A is the action actually happened by this players in KGS. Okay. The goal of this supervised learning, P sigma, is to mimic, to follow the human move, actual expert move. It's not to win. Okay. So it's after training, you test your policy to 1 million positions, and just count how many predictions are identical to the move the experts actually made. And they say that they achieved, basically they use a stochastic optimization here to increase the accuracy of, accuracy meaning the human expert move. And so they achieved about 55% test accuracy, or 57% training accuracy, and 55% test accuracy. And this is better than 40%. It was then best, before the publication of this paper. And it took about 3 weeks using this much computation. And computing the move is just takes 3 milliseconds. As I told you, we need much faster policies for rollout and expansion. So this one is trained using, somehow, they used 8 million positions from another server. Maybe they did this before they did deep learning. That's my guess, because there's no reason to use different sets. You see here, they didn't use any joseki or opening move or standard sequences. In Korean, it's called 정석. No joseki was provided, not explicitly. Because these players are very strong amateur players. They know most of the joseki. And when there's a new style of joseki comes out, I think will try. So in that way, indirectly, it is included in the game, but never as a pattern. Like if you remember the game between Deep Blue and Kasparov, they use a lot of handcraft knowledges into the program. So it's very important to understand that here they didn't use any very little amount of specialties of the game. And that's why they claim that this can be applied to any task. Okay, and so this one is a fast policy. It achieved only 24% of the mimicking the human expert moves, but it's like more than 1,000 times faster. So these two policies are very similar, but the second one is more input features. Yeah. And I will also come back for the value network. The architecture of the value network is very similar to this deep convolutional neural network. So the computing time will be also similar for this. Okay. So this is the only slide that I'm showing some of the supplementary data. So basically, each plane is 19 by 19 both positions, and there are 48 or 49 number for each position. So the input features to these two networks is about this. Okay. So the first thing they did was to copy as much the expert moves, right? And they achieved 55% of the accuracy. And the second thing they did was, because if you think about human plays, it contains some errors or many human factors there. So they wanted to make more robust policies, just not copying expert moves, but they start from these policies, but they improved it by head-to-head gameplay. Here they wanted to, this P sigma was to learn expert moves, but this reinforcement learning is to refine this in such a way that it can win against similar policies. Okay? So this is trained to win. Okay? P sigma was not trained to win. Okay? And so they pick two policies, the same architecture but slightly different parameters, and play many games. And each game is won or lost. And then this result is used to optimize the parameters. There are many parameters in the neural network inside. Okay? And it took, this one took less time, but the calculation time is also about I mentioned it already, 3 milliseconds. Yeah. So when played head-to-head, this reinforcement learning won 80% games against this P sigma. This P sigma was learning the expert moves, right? And this one, so this Pachi, I don't know how to pronounce. Pachi was is the strongest open source Go program, ranked 2 dan in KGS, and it uses Monte Carlo tree search method. But here, P sigma, using P sigma means it doesn't do any searching. Just each time it's just following one selection, right? Surprisingly, this won against this game in 85% of the cases. And this should be compared with 11% previous best. Okay? So you think this P sigma is better than P raw reinforcement learning is better than P sigma, but they don't use this in the AlphaGO. They use this to train value network. And this is very important. I think this was very smart. Okay? At the end, I'm going to discuss this. So this policy was never used in the game of AlphaGO. But it was used to train a value network AlphaGO use. uses, okay? Okay, so here, the value network, this is another concept that this AlphaGO paper introduced, new. They play thousands of games head-to-head using policy. So this is open source program. So they can run this program in their computer. Yeah. So it's very easy. Yeah. Okay, so I told you that this V value star is the optimal value function on the perfect plane. We don't have that, okay? So we want to have something close to that. And the way they do is that they are going to train a machine to give a number between 0 and 100. It's higher than 50, it means it's winning. Less than 50 is meaning it's losing. For given board position. Okay? This is not any action. After action is taken, evaluate the value of that position. Okay? So it's going to approximate this one with, but for this, you have to provide some policy how to play the game. Because from the given position, how do you know which one is winning? The only way is they have to play the game till the end using a policy. Okay? So here, the S is the board position. And if you play this game till the end many, many times using this policy, that's the value of the current position. Okay? So for this, they used reinforcement learning policies. And they define it as their value network. Okay? So here, playing the game till the end using a same policy and stronger policy and without making any silly mistakes is very important. Right? It can be repeated many, many times. So if you look at human games, even professionals make sometimes silly mistakes at the end, near the end or in the middle game. They make some mistakes. And then the value of the many positions should be revised by that, and they don't have, it cannot be assessed by computer, which one was the mistake and something like that. So they have to use a policy, and they use these reinforcement learning policies to obtain this value position. Okay? So again, here, the training, because the Z is the outcome, win or loss, they use, again, the convolutional neural networks to train waves of this value network so that minimize mean squared error between the actual output and this is you obtain by playing out till the end. And what is the current position? Okay. So you minimize this. Stochastic gradient, using the stochastic gradient descent method. Okay. So, but here, this designing game is, I think, very, very smart. So they didn't use any human-played games for this, because humans can make mistakes. Right? So they made 30 million games head-to-head between. So at the beginning, the first move here, U is a number random between these numbers. So first U minus 1 moves, it's played by supervised learned policies. And then, according to this policy, and then there they make one random move. This is very important. You have to make one random move. Okay? This will be apparent when I show the example. And then from there, you finish the game using the supervised, reinforcement learning. Okay? Because this is I already told you that this will be evaluated by this reinforcement learning. Okay? And then the final game is scored by the result. And only single example, okay? At this stage, after random move, what is the state, the board position, and what is the result at the end of the game is added as a one instance. And they generated this 30 million instances, one per one game. One per one game. Okay? So you played up to u minus 1 according to this supervised p sigma, right? And then one position u is random. Okay? And then it will make one move, and it will assess the value of all the moves. Yeah. Yeah.
So game starting with that move, and then result is called.
Yeah, result is based on this policy. Yeah. Okay. So you see that the first two moves, the steps are very. It encourages more diverse games. Because obviously this one is very diverse, uniform random move, right? And this human expert moves are more diverse than reinforcement learned policy. Although when they play head-to-head, the reinforcement learned policy is stronger. The diversity of the moves are higher with this P sigma. So yes. So this theta is the parameter. So here sigma and rho and theta, they all refer to a set of parameters used in the deep learning. So if you think about neural network, there are many ways, right? In deep learning, there are even more ways. So you have to adjust those ways to optimize, for example, this. Okay? So here, this is not a single value. This is many parameters are represented by rho for reinforcement learning, and sigma for the supervised learning, and theta for the value.
Is the parameter something you have to optimize?
Yeah, you have to optimize all. You have to, at the end, you have to construct a neural network, deep neural network. Yeah, there are many thetas there. Yeah. So at the end, you just have to have one set for theta, one set for sigma, and one set for the. Yeah, with that, it played Isidore, yeah. But P rho was not used to play Isidore. Or Fan-Hui. My guess is that AlphaGo used the same, almost identical machine to play Isidore compared to Fan-Hui. Maybe they used more computation. Okay, so I'm going to, this is the tree that I showed you at the beginning, right? Oh, no, next one, yeah. This is not the tree, okay. So this shows all the components used in the AlphaGo. So using these human expert positions, right, you first train a move that mimics the human move, okay. So these three are using deep learning, supervised learning policy network, and this one is just shallow learning, because you have to do fast. And from this, you play against each other with slightly modified parameters. Okay? Sigma. The only difference between this and this is P sigma and P rho is a different parameters. And then by self-playing between this reinforcement learned network, you this is already here. This is playing against each other, self-play, and then from here it generated positions by 30 million games, one from each game. Okay, and then from these positions it generated the value network. So they use two policies and one value network. Okay. The important thing is that this one is trained to win, and this one is trained to mimic the expert moves. Okay. And this at the end, each position will be valued between 0 and 100, estimating the expected outcome of a position. Okay. So here, if you use a policy network, you can use either P sigma or P rho. Each position, each legal positions have probability. All of them have probability. If you add up all the probabilities, it will be 1. Okay? So this one is higher probability and so on. These are also all have probabilities, but it's very low, so it's basically 0. But it's never exactly 0. Okay? Here, this one, you see here the input is basically an action for given S. But here the input is just a board position and evaluating that board position. Okay, so this is the actual AlphaGO's method to select a move. Okay, so I already told you this selection and evaluation and expansion and backup. So here, you have to first choose one leaf node following your selection policy. Okay? Here they used Q plus U. Okay? At the beginning, Q is 0. Q is 0. At the beginning, you have only U. Okay? And at the beginning, because N is 0, U is same as your policy. They call it prior policy, prior probability, and they use the P sigma. They also use the P rho. P rho is stronger than P sigma, but they found that using P sigma make AlphaGO's. Okay, so they use P sigma here. So at the beginning, the first leaf node will be obtained just following P sigma. Okay, so they said, let's say 20 moves, and it goes 20 selections, and reach at the leaf node. Okay? And this leaf node should be assessed in 2 ways. First one, following the conventional Monte Carlo tree search, play out till the end using a policy. Here you have to use a slow policy, fast policy. You have to do this many, many times. So they use the P fast, pi. Okay? But also they have this value network. If you give this board position, it will give you the probability of winning. Okay? So they have to use they use linear combination of these two. This one is win or loss, win plus 1, loss minus 1. Outcome of this rollout. And this one is a number that is guessed from this value. Okay? So then here, these outcome will update Q. At the beginning, Q was 0, right? But here, the Q is basically average of that action, this action and that action, this path, right? With this V. V is just as this. You just calculated this V as L, leaf node. This leaf node value will be propagated up to the root. So you can imagine that at the beginning, it just uses its P sigma. It's more diverse than P raw, and plays game. And then the rollout will determine the value of Q, right? And so at the beginning, it try to search diverse moves. And if you see repeatedly lost games are coming from this edge, then it will be weighted down using this. Capital N is, you see, this is summation of 1. If this edge, this is S, comma A is edge. How many times this S, comma this edge is visited? Okay. So if you think about, at the beginning, it's just a tree with one thread, one of this. And then if you think about creating a tree with a depth of 20, and let us assume that the just branching factor is 2. Right? Then the number of leaf nodes at the end of the tree, you have to do just about 10 to the 6, 1 million leaf nodes. Right? For each of them, you have to evaluate P sigma, because roughly, all the edges have to be evaluated by P sigma. You don't have to repeat it. Once it's past that situation, then it skips. Also, you have to evaluate this value. Right? And then, this can be visited many, many times, up to 40. After 40, it expands. Tens of rollouts should be simulated. Each rollout will take roughly about 100 moves to finish the game. So how many evaluation of the P sigma and V theta and P phi? I just roughly calculated this. So million times of 1 P sigma, 1 V theta, and this many P phi. That's about 3 hours using one GPU. So maybe if you use many GPUs, you can, if you use about 200 GPUs, maybe you can finish this within 1 minute. Okay. But I'll show you the real situation where AlphaGo did go as deep as 27. So maybe my number is off, but in that instance, AlphaGo went as deep as 27 moves. Here, okay. When did I start? Really? Okay, so I have a few more slides, yeah. Okay, so this is an example in the Nature paper. Okay? So for given both position is shown here, black and white. And blue circles and red one is legal moves available. So for each position, it calculates the value. Okay, so the darker blue has a higher value. Okay? This one is 54, highest in terms of value. Okay? More than 50 means it's winning. And this one is 50 and 51. Numbers, like here, low numbers are, obviously, shown with gray color. Okay? And if you use policy network here, then you get also numbers. Okay? So sum of the probability is 1. So this one is 60%. This one is 35%. This one is 0.5%. So anything above 0.1% is shown here. Position not shown with numbers is less than 0.1%. You add up all, is 1. Okay? So contradicting between policy network and value network. Right? So they follow this tree, and selection is by the count. Here, the selection is here. Selection level is here, right? So which was mostly visited. That's the selection. So this is the selected, the count. This was visited 79% of the cases. 20% here and 0.1%, 0.1%, and then all of the rest is 0 or almost near to 0. Okay? You can do this. So this is following the AlphaGo method. Here, AlphaGo method use lambda equal 0.1, 0.5. So this equal average, average between these two numbers.
Most visited meaning in the stage of learning in the past?
So this is not a learning. This is just performing the prediction. So you see, you have to use, this is not the learning. Learning means all the parameters here are sigma and theta and rho. It is already fixed. It took 5 weeks for them to get that parameter. But here, it takes 3 milliseconds to perform one p rho or p sigma. Okay? So I showed here at least million selection. So million selection should go through one of these positions, right? And this out of million times 75% was gone through this. Yeah, I think it's more than million, but yeah, right? Branching. Yeah. These two is not the AlphaGo method, but they repeated the same thing with using only value or only the rollout result. Okay? So if you use 3 evaluation using only the value network, 54. Okay? And based on 50, 51, but the 47, and so on. If you use only the rollouts, okay, the reinforcement rollout, this is 55%. You see, here the policy probability here is less than 0.1%. But this can be chosen because if you do rollout and if you lose, this is -1. So this becomes negative. And then it encourages to go other path. So it's possible that this is the best in terms of tree evaluation from rollout. Okay? The interesting thing is this one. So this is the actual game. In the actual game, so obviously AlphaGo chose this move, and then when it chose this move, this was its expectation. The best move for white will be this next, and the best move for black here, 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 and here, up to 27. This is the from Monte Carlo tree search of AlphaGo at that time, which path was the most visited path, up to 27. This is very similar if you watch Baduk TV. When they give, if this happens, what is the situation, and so on. This is, and I was surprised that they went to up to 27. It's 7 more than I tried to simulate here. Right? So probably the branching is sometimes less than 2, for example here, and so on.
So 27 includes the partners that work.
Yeah, all the partners move, and this is the most probable path. If optimally, they play optimally using this. Yeah. So I have just 2 more slides. So you see, using this supervised learning policy, P sigma performed better than P row. P row was not used, okay? Because this one was actually suggesting more diverse move. But this was optimized for probably for single best move. It's not going to work for tree search. And here, they don't follow the maximum action value position. They go maximum visit count because they found that this was more robust. And the important thing is that the search tree is reused. You see, if Fan Hui played here, actually Fan Hui played here, and at the end of the game, he didn't like this move, and he examined it. He found that this was the move that he should have done. Okay? But if Fan Hui moved here, all these trees are still there, and it keeps. All the rollers, everything is kept. Okay, this is very important. And the subtree below this is retained along with all the statistics, win, lose, rollout, everything. Okay? And obviously, something not visited cannot be visited again, so it will be deleted. And you see, AlphaGo continues to search during the opponent's move. Okay. So if you compare this with Deep Blue, what Deep Blue did against Kasparov. Okay. This Deep Blue used many handcrafted information. But here, the evaluation was 1,000 times less. So in Deep Blue, I think they did in the order of a billion or close to billion evaluation, position evaluation. Here they do order of million, I think. And but by narrowing down the breadth using intelligent policy network and also better evaluation of the outcome using their value network. Okay? Because I told you, so this can be has a potential to be applied to any artificial intelligence, really, or games, anything. Because they didn't give any information or 정석 or something like that. Okay? And no declared professional games were used. Okay? And also, out of this 160,000 games, more than 1/3 is handicapped play. Okay, so I try to follow as closely as I can to the paper. So this is my thought. Okay, so I already told you that the designing this value network using not using reinforcement learning, but using supervised learning was critical, I think. And because a human can make silly mistakes, and this data they created has no such mistakes. Computer does not make any mistakes. It just follows what is given. Okay?
Well, human is given the exercise paper.
Yeah. Okay. So I think as of today, in most of the areas, computer can do better than human. And the area where the AI has problem is maybe voice recognition or image-related things. I could be wrong, but so this is, I think, quite significant. And as I told you, if the game follows the most visited sequence of moves, AlphaGo can explore its next moves even deeper. Okay. So if you remember, maybe if you watch the game 4, right? The only victory of Lee et al. The move 78, called the divine move, was not in the AlphaGo's tree search. So, because the situation, AlphaGo had to remove all the trees it already generated. Everything it has to start from scratch from there. It's my thought. Okay? Based on my understanding of this, reading this paper. Okay? And so it used more time, but only a few minutes, right? So all the moves he considered was shallower than all the previous ones. And so this was not a bug. It's the same thing. If your opponent plays something you never expected, you have to re-evaluate everything, right? So, one thing that I wanted to discuss. So, some experts mentioned that Lee et al. should not play Joseki of long sequences. I don't think, maybe that should have been the policy, I mean, the strategy of the Lee et al. Because the Joseki was not included explicitly. Okay? And if you think about the potential application of this method to many different things, but that includes medical-related things, diagnosis of Lou Gehrig's disease and so on. You can visit this website. And this is mostly using machine learning to do better decision-making for medical industries. Okay. Thank you for your attention.